Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is a follow-up to the previous video in which we computed the RMS based on pretty much the definition of RMS. In this video, we are going to optimize it because no one really does the computation following the definition directly like we did in the last video. Everyone does the RMS computation in the way that we are going to do in this video. So let's jump right in. What we have here is the previous implementation, the existing one, and it's computing RMS using this code. The first thing that is bad about this code is that I think I forgot to explain the effect of the window size in the computation of RMS. So let's take a look at this. So when I change the window size, the RMS meter is going to respond faster or more slowly. So as I increase the window size, and I don't think I remember to do this on the last video, if I increase the window size, then you can see that RMS is moving more slowly, but if I decrease the window size, then it's moving faster. And there is a bug in the code that if I take the window size to 0, which is something that I allowed you to do because I modeled this after recomp, and recomp allows you to have a window size of 0, then there is a bug in the code. The bug is, if the window size in milliseconds is 0, then here on the slider, when we compute the window size in samples, then we multiply 0 by the sample rate and we get 0, which is a window of 0 samples. And if you compute over a window of 0 samples, you're not doing any computation at all. So what I want to do is to have at least one sample in the window. As you can see here, when I take this value down to 0, then RMS just stops computing, and that is not what we want. So the solution here is to take the maximum of 1 and whatever you compute. So if this value turns out to be 0, then we get a window of at least 1. When I save this, and now we can look at the plugin again, and it's moving super fast, but at least it's computing RMS. So that is a bug from the previous episode that we fixed just now. Next, let's consider what we can do to make this faster. Because we had a solution that kind of works, and that is to only compute RMS every so often. We put the computation of RMS here in this GFX block, and that only runs 30 times per second, which is a lot less than the 48,000 times per second that the sample block runs. But there is a better solution, and if we implement this better solution, then we can even calculate RMS on every sample. And I want to implement all these different versions, the one from the previous video, the one in this video, and the one in the next video, all in the same effect, so we can have not only the computations of RMS, but also we can compute the difference between the different methods, and we can see if we are introducing any errors by deviating from the definition and trying to implement these optimizations. So what we are going to do is just add new code to this effect. And the first idea here is we are computing the square of all the samples. When we are doing the sum, we are squaring the samples. And anytime you square the value, you get the same output. So what if instead of storing samples and then computing its square every time, what if we stored the square of the sample already? And then we don't have to compute the square every time. You can just add the squares they are already in the array, already in the window. So we're going to have a new window, and that window will be after this one. So now the window of squares will be after this one, so it will start at this position, because that's the position of that's the position where the window ends. So the window's squares will start on that position, and then the size times 2 is the amount of memory that we are actually using. And the window pointer can remain the same because the size of the window is the same. We are just storing something else in the window. Now we have two windows side by side in memory. Okay, so we already have a window of squares, and the pointer into the window will be the same. It will be reused. So what we want to do is window squares add window pointer will store the square of the sample. And we are still only looking at the left channel. It's something we are going to address in a future video. So now we have two windows side by side. They are storing the samples and the square of the samples. So here in the GFX block, we are computing RMS. And I'm going to put some code here that will be the window sum squares 2, because we already have one here, and we are doing the addition of the squares over here as well. And I'm doing this here in this block because I don't think that our implementation will be fast enough now on this first step. This video has a few steps that we are going to go through. In this first step, I don't think it will be fast enough. When it is fast enough, then we'll try to take this block out of the JFX block and into the sample block, and we'll see if we can compute RMS for every sample and still run in reasonable time. Because as you remember, if you take this code and put it in the sample block, we did that in the previous episode. In fact, that's how we started. It is so slow that you can hear the samples being dropped. The audio starts to be flaky. Okay, so now we have this, it starts with 0. We do a similar setup to the one we have here, but instead of adding to the sum of squares, we add to the sum of squares 2. And instead of taking the square of the window, we look at the window of squares. And now we have the sum of the squares. We have to do this computation as well at the end. So this will be RMS amplitude optimized. Oh, so yeah, why not we call this all optimized instead of 2 optimize? I think it's more meaningful this way. It makes more sense. So now we are looking at the RMS optimized as well. So I think we should have another slider to show that value. So we have already a value here, a slider for RMS. Let's have another slider. It will be slider 4, RMS optimized in dB. So this will be optimized. And I think I will call this definition or definitional, because we are following the definition of RMS to compute this one. So we should probably rename all these variables to read as definitional. And now we'll have like a window of samples or window definitional, something like that. We'll see. Later we'll take care of this. So now what we want is to change this RMS optimized dB to be something, and I think I'll bring this computation here up so the blocks really are separate, and I'll leave a new line here for the optimized part, and I'll also leave here an annotation that this is the definitional. Also, this comment doesn't apply because we are not doing the sum and dividing by the size. We are doing a sum of squares and dividing by the size and then taking the square root, so that comment was stale. Okay, now we kind of copy this to here, and the slider that is changing is slider 4, and we don't need this part, and what we want is this variable. Just a bunch of renamings. Oh, and it's important that we remember to change this one as well. It should be using the window sum squares optimized. The samples, the window size remains the same. And then everything else here makes sense. So when we save this and we look at the plugin window, now we have two computations of RMS going on here, and they are not doing anything. So there is a problem. Okay, that is weird. When copying and pasting stuff, for some reason I got some part of the code out here. So we can easily fix that by getting this part, copying it back, and then using the amplitude here. And now we should be good to go. Let's save this, and we start to see the definitional one at least is moving. The other one is not, so there must be some other issue as well. Oops, the issue is right here. I am using the wrong index in this place. And then when I save this, now we can see both moving simultaneously. They are in tandem, which is what we wanted, right? We wanted them to be the same computation, just optimized faster. But they are computing the same values, so they should be moving together. And they are. Great. There is still more things we can do to make this even faster. Let's think about this addition. What we are doing is, for every time we want to compute RMS, we are going over the whole window and adding up the values. And the thing is, when you are adding like 5 numbers together, the output is always the same. The result is always the same. And we are only changing the window one sample at a time. So, and we are changing the window here, one sample at a time. So it's as if you are adding 5 values. Suppose that the window has a size of 5. So we are adding up 5 values, and that is a certain number. And then you're changing one of the values. All these 4, when you add them up, they are still amounted the same. You're just changing one of them. So the idea to optimize this computation is you store not only the squares of the samples, as we already did, but you also store the sum of all the squares. So we are now computing the squares, the window, and their sum. And when this value changes, what we do is we subtract the old value and we add in the new value with the new sample. And this way, we are not going over the whole window to keep track of this sum. Let's implement this. So first of all, I want to have here on initialization a window squares sum, or I'll call this the running sum, because we are changing that as we go. It's different from this one, which is computed from scratch. That's why I'm calling it the running sum. And it starts with 0. And then here, when we are doing this, what I'm going to do is, first of all, in the running sum, I'm going to subtract whatever was already there. Then I am going to add back whatever is the new value. So on this line, if you remember here, the idea with my hand, what I'm doing on this line is taking out one old value that was already there, because I am about to overwrite that position. And then I am going to add back the new value on this new position, the new square on this new position. Excellent. Now that we have this, we don't need to compute this whole sum. We don't need to make this part of the computation, because we already have a variable that has that value for us. We can just look at it. So the running sum is this. And I should probably call this optimized to make everything, all the variable names have optimized in their name. Anyway, so yeah, this is already the running sum. We already have it here. So if we want to compute RMS, all we have to do is divide by the size of the samples, the size of the window, and take the square root of that. Now let's take a look at the meters, and they are not agreeing. Yeah, this one is staying at -16, so there must be some issue. Let's figure this out. Okay, so that was weird, but it was kind of easy. All I had to do to fix this one was to do a full compile reset. There was some junk somewhere. I don't know. I don't care. But I just full compiled and reset, and now they're still moving in tandem. They are still moving together, though they are computing the values very differently. Okay, so now I promised that this would be fast enough for us to compute on every sample. And I'm going to move this block up and prove that to you. But first, let's consider whether you want to do that in your specific case. It depends. If you're computing RMS to have some kind of slider in your interface to show something to the user, then you may not need to compute RMS on every sample because you're only moving the slider every so often. You're definitely not moving it as fast as you are computing new samples. But there are cases in which you want RMS to change on every sample. Maybe you have an effect that has to do with loudness or with levels. Maybe you are doing a compressor. And in that case, you want your compressor to be able to react on every sample. You want it to be able to change the attenuation on every sample potentially. So you want to compute RMS for every sample. So let's move this block up here to the samples block and save this. And we are still seeing them moving in tandem. Not quite, because now the RMS optimized is moving. It's being calculated more often, so it is moving just slightly ahead of the definitional one. Because it is computing more often, it's going faster to the place where it should be, because the computation is telling that the RMS has changed, and the definitional one has to wait a little until it picks up. But in any case, the point here is that we should be able to put in some signal, like the sine wave we had before, and it shouldn't be crackling anymore. Okay, so let's put in the tone generator right before this one. It doesn't really matter, actually, if it's before or after, because the computation takes so much CPU, and we can already see that it's not taking any CPU at all. Just because by the virtue of doing these optimizations, it's not taking any CPU at all. But if the effect is taking CPU, it's going to introduce crackles, even if it's after the effect, even if it's before the effect. So if the tone generator is here, and the RMS is too slow, it's still going to introduce audible problems in, even if the thing that is causing the CPU lag is after. It doesn't really matter. It's just that the whole effects chain gets too slow. Anyway, so with that, we can turn off monitoring. And now the only thing we should hear is this tone. I'll bring it down, not to blow our ears. So I'll do it in -30. And I will unmute. Something I did before I even started recording, I muted the master track as we usually do. There you go. I can hear the tone. It's not being affected. I can look at the CPU use. It's not that much at all. So there you go. With these simple optimizations, what we are doing is computing RMS on every sample, and we are still doing that with almost no CPU at all, just because we are not going over the whole window every time. The next thing I want to do is to go over the code and change the names of the variables everywhere to make them reflect what they are. So when something is in the definitional part, I will put definitional in the name. In the optimized part, I'll make sure that it has optimized in the name, and I'll do that and get back to you in a second. Okay, I'm back. I just spent some time renaming everything, and now everything that has to do with the definitional version has a variable that ends in definitional, and optimized, same story. But there is still some things that I want to talk about before we finish this session. And that is, well, the first one is that we have done something here that may cause problems, but in our case won't cause problems. But it's something you need to be aware of in case you read about this on the internet. It has to do with this part. When we are computing the optimized version here, what we are doing is we are taking the sum and subtracting the current, or really the old one that we are about to overwrite, we are subtracting it. But we are doing this with floating point numbers. These are numbers between -1 and 1 that are floating point. And it is usually a problem, but in our case, I don't think it will be. The reason why I say that it's usually a problem is that Floating point numbers don't have that property I was talking about before. Remember, I said that there is a sum of all 5 samples and you take one out. Well, usually with numbers in mathematics, if you have a sum and you subtract one of them, it's equal to the sum of the other 4, and that holds in mathematics because addition and subtraction are associative, they are commutative. I don't really remember the technical term, but it has this property that you can take the sum of the 5 numbers, subtract one of the 5 numbers, and you get back the addition of the other 4 numbers. That is not the case for floating point numbers. Floating point numbers are not like mathematical numbers, they are weird numbers. And if you add things up and you subtract them back, you may not end up where you started. Which is terrible, because if you do this, then you have some junk in this Windows sum optimized that's never going to go away. That junk will be there forever because we are never resetting this variable in any way. We are always subtracting and adding to it, but if there is some small number, some reminder of junk, it will be there forever in the computation. Usually that's a problem. And there are different solutions for this. The first is probably the simplest, is just every so often you recompute using the definition. So you would, for instance, here on the GFX block that is running a lot less often, then you maybe would come here and do something that amounts to the same as this. You add everything back together, and you don't even need to use a window of samples. You can use a window of squares of samples, so you can use the window optimized, and there is no need for another window. You're not paying extra memory for this. And then you don't square when you're doing the addition, but the idea here is we are adding everything back up together and we are resetting effectively the window every so often. And you could do that maybe every second, maybe every minute, something like that. You just every so often recompute the window from scratch and you get rid of the noise in the subtraction and addition. That's one way of solving this. Another possible way of solving this, I'm not even sure that this is the case, but I think that another way of solving this is checking whether you end up with a number that is negative here. Because remember, we are adding squares. We are adding the squares of the samples. So you're never supposed to have any negatives. So if you are adding things and then subtracting them back together and you end up with something negative, that is junk. For sure, definitely. So you could check if the Windows sum optimized here becomes negative, and then if it is negative, then you can truncate it and say that it's 0. I'm not even sure that this is a solution for this problem, but I saw some JS effects that have been written by Cockles, and it seems like they're doing that. Maybe it is to fix this. I'm not even sure. But I have another working theory for why that is not a problem for us. And it has to do with something we talked about in the previous episode. It's a mystery. So here I have the effect, and it's running on the sound of my voice. As you can see, it's going up and down. But I can turn off monitoring, and now there is no signal coming through. And yet we have some readings here, some weird numbers. Where are they coming from? The solution for the mystery has to do with the idea of samples. So if you look at the sample 0 here in the debug window, sample 0 is 0. In fact, every sample is 0, but in particular, sample 0 is 0. So here is an experiment. What if in every sample, I'll have a variable called experiment, and I'll just look at the addition of sample 0. I haven't saved this yet, but just think about this. I'm adding zeros. I should see 0 as the result of this variable, right? So now I'll save and we'll look at the experiment. And you can see that it's very small, but it's not really 0. And it's growing, which means that every sample is not exactly 0. Why is that? Well, it has to do with an optimization, a problem that happens with the computation of floating point numbers. Usually, if you have floating point numbers that are reasonably sized, I'm saying numbers like maybe even this number that is very small, but it's reasonably sized, if you have these kinds of values, then floating point computation is super fast. It is probably the fastest that the computer can make. Probably not as fast as integer computation, I'm not sure, but definitely fast. Processors have been optimized to work on floating point numbers like that, so it is reasonably fast. But if the number is super small, I'm talking about very small numbers like the ones that we are seeing here, then, or maybe probably even smaller than that, then the processor goes into, oh, okay, if you care about this computation, I'll do it for you and I'll do it as precisely as I can. But I will be super slow in doing it because it's not something that I do often. I haven't been really optimized to do this. This problem is terrible if you think about it, because if you have values that are very small, then your processor will be computing them very slowly. It will drag the whole computation of everything you care about for these very small values that you don't really care about. And this is an issue called normalization or denormalization. And the solution for this in JS effects is that every sample comes with a very small noise. And that's what we are looking at here. We are seeing that noise adding up over time. You can tell that it's very small because I'm running this experiment 48,000 times per second, and it's adding up all that noise. And still, after me speaking for, I guess, a minute or two here, it is still a very small number. So we're talking about adding a very small noise to the samples. And when it's doing that, it's guaranteeing that it's above that threshold and the processor is still fast when computing these kinds of floating point numbers. But if you end up with, for some reason, for instance, with this computation, when you're subtracting values and whatnot, if you end up with values that are very close to zero, super small, but not zero, you don't end up with the problem of denormalizing. You don't end up with computations that are too slow, because Reaper is adding for you that very small noise. And in doing so, I think it is also fixing the mistake or the problem of ending up with junk, because it's adding random noise. It's not just a fixed amount of noise, it's random noise. It's like white noise, which we saw in a previous episode. So it's like white noise, and it is adding a very small amount of it. So you are never able to hear that, not even if you add everything up for a long while. But I think that by adding that small random noise, it's getting rid of the junk. If the junk is 0.00001, then at some point, Reaper is going to add minus 0.0001 and compensate for the junk and get rid of it. So that's why I said that it is a problem to do things this way naively without resetting the sum from time to time. But I think it's okay in this case. I definitely have never been able to experience the problem of the junk getting in and making something go bad. But it's something to be aware of. If you read online about denormals and you're writing JS effects, you probably don't need to care about it. But what if you do? Think about it. What if you don't want this very small noise for whatever reason? Well, here's something you can do. You can come here to the init section and you set this special variable to 1. And when you do that, you can see I did a full compile reset here. And now experiment is exactly 0. And in our case here, the RMS computation is exactly 0 because it's going over through the rest of the code, and it doesn't have a small amount of noise. So it's actually trying to do something like the log of 0, which is undefined. And it amounts to being 0 here in this case. So if you really care about denormals and you really care about that small amount of noise, you can turn this feature off. But I won't, because I think this kind of solves our problem. And I think overall it's just better to not mess with this. Now the experiment, you can see that it's no longer just 0 because I took off that special variable. But yeah, it is a small amount of noise. I think it's solving a problem for us. It's definitely solving the problem of what happens when there is no signal coming through. You still have some reading, which makes sense. I mean, if there is no signal coming through, you could say that it's minus 300 dB, which is effectively silence. And that gets rid of the whole denormalization problem for us. And there you have it. In practice, that is how people compute RMS for things like compressors and so on. They usually use this optimized version, not the definitional one we came up with in the previous episode. There's still more I want to talk about in terms of RMS. In the next episode, we are going to implement RMS yet again using yet another technique so that you don't have to keep around that window of samples or the window of squares of samples. It is just one variable that you have to keep around, and it will not be as precise as these two versions. We'll look at how much precision we are losing in the process, but it's definitely faster. You consume less memory. It is simpler to implement, and it is kind of weird mathematically, so it's kind of interesting to look at. And there are some plugins that do this. I looked at the source code for all the plugins that come with Reaper and some of that are available in Repack. Most of them are doing the computation of the window the way we did in this episode with the optimized version, the squares being stored and the running sum. For instance, the Cockles plugins do this. But there are some plugins that do it this other way, and it's kind of interesting to learn how it works. The Auto Mixer plugin does that, not the one I created, but the one that existed before that. And if you want to learn more about this, check the other videos in this channel. Also, some Stilwell plugins seem to do the computation of RMS in this other way we are going to cover in the next episode. And I think that the Tri-Leveler by Sonic Anomaly also does the computation of RMS using this method, though that code is going over my head. I don't fully understand everything that's going on there. Anyway, thanks for watching this video. I see you on the next one. If you're interested in these kinds of things like programming and Reaper and audio effects and even other things that are related to video production and whatnot, then make sure you subscribe to the channel because I have many more videos coming up. And that's it for now. See you on the next one. Bye.